We're going to see how Taylor series can help us solve some problems that we've seen previously that might have been more difficult to solve. Let's start by looking at the limit as x goes to 0 of 2x squared plus cosine of 2x minus 1 over x to the fourth. Note that if we were to plug in 0, the top would go to 0 plus 1 minus 1, which would be 0, and the bottom would go to 0. So we would have a 0 over 0 indeterminate form. Now we could do L'Hopital's rule, but let's try instead looking at the Taylor series for cosine of 2x. So we could rewrite this as the limit as x goes to 0 of 2x squared plus, now cosine of 2x, we know the Taylor series for cosine of x, it's 1 minus x squared over 2 factorial plus x over to the fourth over 4 factorial minus x to the sixth over 6 factorial plus dot dot dot. It goes on and on like that, right? But now it's cosine of 2x, so we're going to put a 2x in each of those spots where the x would go. And then, so that's our cosine of 2x, and then we do minus 1 divided by x to the fourth. And what can we say then? Well, we have a plus 1 here and a minus 1 here. So we can add those together and get 0. And we also have a 2x squared here, and we have a term here that's an x squared, so let's think about what that's going to simplify to. That's going to simplify to 2 squared, x squared over 2 factorial, which is 2. So this is going to simplify to 2x squared. So these two terms are going to add to 0, and we're going to be left with the limit as x goes to 0 of 2x to the fourth over 4 factorial minus 2x to the sixth over 6 factorial plus 2x to the eighth over 8 factorial plus dot 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 over x to the fourth. But now we can divide everything through by 1 over x to the fourth, or maybe factor out an x to the fourth on top. Might be easier. Let's try that. So let's do limit as x goes to 0, and let's pull out an x to the fourth. So now we're looking at 2 to the fourth over 4 factorial minus 2 to the sixth x squared over 6 factorial plus 2 to the eighth x to the fourth over 8 factorial, etc., over x to the fourth on the bottom. Now, canceling those x to the fourth because the number over itself is 1, we are left with looking at the limit as x goes to 0 of 2 to the fourth over 4 factorial plus 2 to the sixth x squared over 6 factorial plus 2 to the eighth x to the fourth over 8 factorial plus dot 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 dot. And note that this term is multiplied by x squared, so it's going to go to 0. This term is multiplied by x to the fourth, it's going to go to 0. And all these other remaining terms at the end are also all going to go to 0 because they have powers of x in them. And the only thing that's going to be left is that 2 to the fourth over 4 factorial, which is 16 over 24, or 2/3. So this gives us a way of finding a complicated looking limit, and it gives us some intuition because we kind of get an idea of what power of x the top acts like and what power of x the bottom acts like, and thus what should happen. Let's try another limit example. We have the limit as x goes to 2 of natural log of x minus 1 minus x plus 2 over x minus 2 squared. Now let's look at what would happen to this if we plug in. We have natural log of 2 minus 1, so natural log of 1, which is 0, minus 2 plus 2, so this is a 0 altogether. And on the bottom, we have 0 squared, so that's a 0. So this is, again, the indeterminate form 0 over 0. So we could try to do L'Hopital's rule, but let's try this Taylor series method again. So do we know a Taylor series for natural log of x minus 1, which includes x equals 2 in the interval of convergence? Well, we could rewrite this as the natural log of 1 plus x minus 2, which would be the natural log of 1 plus u for some u. And we know the power series for that. That's u minus u squared over 2 plus u cubed over 3 minus u to the fourth over 4 plus dot dot dot. And so we can say that the natural log of x minus 1 equals the natural log of 1 plus x minus 2, which is equal to x minus 2 minus x minus 2 squared over 2 plus x minus 2 cubed over 3 minus x minus 2 to the fourth over 4 plus dot dot dot. And what do we know about the interval of convergence? Well, the interval of convergence for this natural log of 1 plus u is -1 less than u less than or equal to 1. So we would have, for our series here, -1 less than x minus 2 less than or equal to 1, which means that 1 is less than x less than or equal to 3. So yes, 2 is in there. All right, so let's try doing our limit this way then. So we're looking at the limit as x goes to 2 of, well, we have this series here, right? So x minus 2 minus x minus 2 squared over 2 plus x minus 2 cubed over 3 minus x minus 2 to the fourth over 4 plus dot dot dot, and then minus x plus 2 all over x minus 2 squared. So note that the negative x plus 2 at the end here can be rewritten as negative x minus 2. So we have a positive x minus 2 and a negative x minus 2. So those are going to go away. And we're going to be left with the limit as x goes to 2 of negative x minus 2 squared over 2 plus x minus 2 cubed over 3 minus x minus 2 to the fourth over 4 plus dot 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 over x minus 2 squared. Now let's pull out an x minus 2 squared out of the top, or maybe this time let's divide everything through by x minus 2 squared. Let's just see how it looks different that way. So we're going to multiply top and bottom over 1 minus over x minus 2 squared. This is really the same algebra trick. And so we get on top negative a half plus x minus 2 to the first over 3 minus x minus 2 squared over 4 plus dot dot dot, terms that have higher powers of x minus 2 in it, all over 1 in the bottom. So what's going to happen? This term is going to go to 0 as x goes to 2. This term is going to go to 0 as x goes to 2. And all these other terms have powers of x minus 2 in them, so they're also going to go to 0. So the only thing that's going to be left is going to be the negative 1/2 over 1, which is negative 1/2. Again, you could check this answer with L'Hopital's rule. It will also work on this problem. Now let's look at the problem. The limit as x goes to infinity, x times e to the 2 over x minus 1. So the x is going to infinity, and e to the 2 over x, that's going to go to e to the 0, which is 1. So 1 minus 1, that's 0. So this is infinity times 0. That's another indeterminate form. And again, we could do this with L'Hopital's rule. It's a little more painful when it's infinity times 0. But let's again see if we can use Taylor series to solve this problem. So can we find a series for e to the 2 over x? Well, we know a series for e to the x, right? So let's try putting 2 over x into it. So we have 1 plus 2 over x over 1 factorial plus 2 over x squared over 2 factorial plus dot dot dot. Now, are we allowed to do that? This is not a power series. We can't have x's on the bottom. These are going to have negative powers of x, so it's definitely not a power series. But it does turn out it's going to work. We do have to worry about one thing, though. We're doing a substitution here. We're letting u equal 2 over x, and we're using the e to the u formula, right? So when x is going to infinity, then u here would be going to 0 from the right side. So instead of taking the limit as x goes to infinity, if we're going to instead look at this new series in terms of u, we want to look at the limit as u goes to 0 from the right, and then actually write our problem in terms of u. So let's try this. This is going to be the limit as u goes to 0 from the right of 1 plus u over 1 factorial plus u squared over 2 factorial. Now it's a power series, right? Plus dot dot dot. Now that's the e to the 2x part. Maybe we should write our original problem in u's before we try to plug the series in. So let's write our original problem in terms of u. So we want to take the limit as u goes to 0 from the right of, well, if u is 2 over x, that tells us that x is 2 over u. So we're going to get 2 over u for that x here in the front. And then we have e to the u minus 1. So now we can use power series. So we're doing the limit as u goes to 0 from the right of 2 over u times, and then we have 1 plus u plus u squared over 2 factorial plus u cubed over 3 factorial plus dot dot dot. And then we have minus 1, and this whole thing was in parentheses. Okay, so now again we have a 1 in the front and a negative 1 at the end. So we're going to be able to cancel those. And so we're going to be looking at limit as u goes to 0 from the right of 2 over u times u plus u squared over 2 factorial plus u cubed over 3 factorial. And you can see in all the problems where this is actually going to work, all of the terms at the end of the Taylor series, that tail, are always going to go to 0. Let's go ahead and factor this 2 over u through. So limit as u goes to 0 from the right. We're going to get 2 over u times u is 2, plus 2 over u times u squared over 2 factorial is u, plus 2 u squared over 3 factorial, plus 2 u cubed over 4 factorial, plus dot 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 dot. And when we take this limit now, we're going to keep the 2, and everything else is going to go to 0. So we get an answer to our limit of 2. Sometimes we can use Taylor series to help us find derivatives as well. Let's say we wanted to find the derivative of arctangent of x, and we didn't already know the answer. Could we use power series or Taylor series to help us figure that out? Well, we know that f of x equal to arctan of x is equal to the power series x minus x cubed over 3 plus x to the 5th over 5 minus dot dot dot, which is the sum, k goes from 0 to infinity, of negative 1 to the k, x to the 2k plus 1, all over 2k plus 1. And that this is valid if the absolute value of x is less than or equal to 1. So x being greater than or equal to negative 1 and less than or equal to 1. Well now, if we want to take the derivative, f prime of x is going to be the derivative of arctan, which is what we want, but it's also going to be the derivative of this power series, x minus x cubed over 3 plus x to the 5th over 5 minus dot dot dot. So that means that it should equal 1 minus x squared plus x to the 4th minus x to the 6th plus dot dot dot. But what power series is this? Well, notice the pattern. This is 1 minus x squared plus x squared squared minus x squared cubed plus dot dot dot. So we're replacing x with x squared, and then we're getting power increasing by 1. And we're alternating signs. So this is a geometric series. Let's rewrite it one more time. 1 minus negative x squared plus negative x squared squared plus negative x squared cubed plus, notice now that we get our alternating signs because that negative comes out whenever that's to an odd power. So now we can see our power series is just geometric. It's multiplying by negative x squared each time. So this is going to be equal to 1 over 1 minus negative x squared, which is 1 over 1 plus x squared, which is what we expected, right? That's the derivative of arctan. But you could see how you could use a similar technique to find derivatives of things you didn't already know. Now let's look at another example. Consider the differential equation at y prime of t minus 3y of t equals negative 2, and we know that y of 0 is 5. And we're going to use Taylor series to try to solve this differential equation. This is one of the most powerful applications of Taylor series. This is going to be a really simple example, but you can take, courses and courses on just solving differential equations, and because they come up quite a bit in applications. So here we're going to assume there is a solution, y of t, and we're going to assume it's a Taylor series centered at 0. So it has, this form of a Taylor series, and we want to find the coefficients. So do we have enough information to do that? Well, what do we know? We know y of 0, and since the power series is going to be c0 plus c1t plus c2t squared plus c3t cubed plus dot dot dot. We know if we plug 0 into that, the only thing left is going to be that c0. Every other term is going to be 0. So we should be able to say we should be able to say that 5 is equal to y of 0, which is equal to c of 0 plus a whole bunch of zeros. So c0 has to be 5. Okay, well that's great, but that seemed like a trick. Can I say anything about any of the other coefficients? Well, remember what we do know. We know something about the derivative. We know that y prime of t minus 3y of t is equal to negative 2. So how can we use that? Well, that means if we plug 0 into this equation, we get y prime of 0 minus 3 times y of 0 should be negative 2, but we know y of 0, so y prime of 0 minus 3 times 5 should be negative 2. So y prime of 0 is going to equal, we're going to add 15 to the other side, so 13. Okay, so now we know y prime of 0 is 13. But just like when we knew that y of 0 is 5, this is going to allow us to find a coefficient. Now we can take the derivative, y prime of 0, of our power series. Maybe let's write that out one more time. So we can look at y of t equals c0 plus c1t plus c2t squared plus c3t cubed plus dot dot dot. Now we can take that derivative. Y prime of t is going to be, c0 is going to be 0 plus c1 plus 2c2 t plus 3c3 t squared plus dot dot dot. And so we know that y prime of 0 is 13, and also that it is 0 plus c1 plus a whole bunch of zeros. So c1 has to be 13. Well, what about the rest of them? What about the second derivative, the third derivative, the fourth derivative? Well, we know that y prime of t minus 3y of t is equal to negative 2. So we know, taking the derivative of both sides, that y double prime of t minus 3y prime of t is equal to 0. And that tells us that y double prime of t equals 3y prime of t, which means that y double prime of 0 is 3 times y prime of 0, which is 3 times 13. And notice that if we keep differentiating this expression right here, we're going to get, y triple prime of t is equal to 3y double prime of t, y the fourth power derivative of t is going to be 3 times y the third derivative of t, and we could keep doing this forever, right? So we found a pattern. We found that every time we take a derivative, we multiply the answer by 3. So in general, we have that the kth derivative of y at 0 is going to be 3 times the k minus 1th derivative, which means it's going to be 3 to the k minus 1 times 13. So we know that for all k, well, k equaling 1, 2, 3, etc., that we found a pattern. We have ck equaling the yth derivative at 0 over k factorial is going to be 3 to the k minus 1 times 13 over k factorial. So we have our solution. It's y of t equals 5 plus, remember 5 was the c0 term, plus 13t plus 3 times 13 over 2 factorial t squared plus 3 squared times 13 over 3 factorial t cubed plus dot 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 dot. But what function is this? Well, let's see if we can recognize it. Notice that once we start looking at this 2 factorial term and this 3 factorial term, we're looking at powers of 3 on top and factorials on the bottom. So what do we know that might look something like that? Well, we know that e has power of x on top over a factorial on the bottom. So what about if we wanted powers of 3 in there too? What about e to the 3t? what would that be? Well, that would be 1 plus 3t plus 3t squared over 2 factorial plus 3t cubed over 3 factorial plus 3t to the 4th over 4 factorial plus dot 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 dot. So the question is, how is that like what we had before? Well, what's different? Well, there seems to be lots of 13, so let's try multiplying everything through by 13 and then see if it starts to look closer. So now we have 13 plus 3 times 13t plus 13 times 3t squared over 2 factorial plus 13 times 3t cubed over 3 factorial plus 13 times 3t to the 4th over 4 factorial plus dot 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 dot. Okay. Well, okay. Now let's compare. The first few terms, notice, are kind of off. We'll have to fix those later. Can we look for a pattern in these higher terms? Alright, so in the sequence we want, we would have 3 times 13 over 2 factorial. We have the over 2 factorial, we have the 13, and we have a 3 squared t squared. We want just a 3t squared. In this one, we would like a 3 squared 13 over 3 factorial. We have the 3 factorial, we have the 13, but we have a 3 cubed t cubed. So we have one more power of 3 than we want in these. So let's take everything in this e expression that we're working with here and divide it by 3. So 13 over 3 e to the 3t is going to be 13 thirds plus 13t plus 13 times 3 over 2 factorial t plus 13 times 3 squared over 3 factorial t, wait, this one's t squared, t cubed. And if we continue this pattern, we would have the next term would look like 13 times 3 cubed over 4 factorial to the 4th, etc. Okay, we're getting closer. Now all the terms after the squared match the series that we want. See that? So we need to figure out how to make the first couple terms match. Well, these first couple terms are just, we can just add stuff to make it match. So we have 13 over 3, and we would like to make that 5. So what's 5 minus 13 over 3? Well, there's a 2/3 difference there. So let's take our y function that we want now, and it was 5 plus, well, look at that, even the 13t is matching. So 5 plus 13t plus all this other stuff. And let's compare it with this series. Well, if we take our y of t series and we rewrite it as 13 thirds plus 2 thirds, adding those together, we'd get 5, right? 15 thirds. Plus 13t plus all the rest of this. Well, actually here, let's change the order of these two and make it 2 thirds plus 13 thirds. All of this part, we know what that is. That's the power series we kind of finagled there, 13 thirds e to the 3t. And so we get that y of t is equal to 2 thirds plus 13 thirds e to the 3t. So we were able to recognize that power series as similar enough to one that we knew that we could manipulate it until it actually matched. Now you could check this answer by actually taking its derivative and plugging it back into the differential equation and seeing that, both sides of that differential equation actually end up being equal. Alright, now here's one of my favorite applications of Taylor series. We're going to integrate e to the negative x squared. And I want you to think about it for a minute. None of the techniques we know so far will allow us to integrate e to the negative x squared. But if we rewrite e to the negative x squared as a power series, Then we know how to integrate it, right? Because you can just integrate power series term by term. So let's rewrite it. We know that e to the x is the power series k goes from 0 to infinity of x to the k over k factorial. So e to the negative x squared is going to be the power series k goes from 0 to infinity of negative x squared to the k over k factorial, which is the power series k goes from 0 to infinity of negative 1 to the k, x to the 2k over k factorial. And now, if we want to integrate it, the integral of e to the negative x squared is the same as the integral of the power series, which is the same as the power series of the integral. This was a big theorem that we had. But remember now, the integral only cares about x. It doesn't care about those k's. So this is just the sum k goes from 0 to infinity of, we keep our negative 1 to the k, we keep our k factorial, and we just take the integral of x to the 2k to get x to the 2k plus 1 over k plus 1. Well, that's a power series. And we can add a constant to that, right? We integrated, so we should add plus c. This is a power series, and it's a function then. So it's an answer to our integral. Now, we don't actually know a closed way of writing this. This is an example of a new function that you get from power series that you didn't have before. The antiderivative of e to the negative x squared, the easiest way to write it is as a power series. All right, now this problem asks us to approximate the integral of e to the negative x squared from 0 to 1 with an error of less than 10 to the negative sixth. Now this makes sense because we have the antiderivative of e to the negative x squared as a Taylor series, and we know how to approximate Taylor series to within a certain accuracy. So let's remember what that Taylor series was. It was the sum, k goes from 0 to infinity, of negative 1 to the k times x to the 2k plus 1 divided by k factorial times 2k plus 1. So that antiderivative of e to the negative x squared was equal to this plus c. So if I want to do the definite integral from 0 to 1 of e to the negative x squared dx, well, that's going to be the indefinite integral, the antiderivative here, evaluated from 0 to 1. So we're just going to plug in 0 and 1 and subtract. Well, this is the sum, k goes from 0 to infinity, of negative 1 to the k, 1 to the 2k plus 1, minus the sum, k goes from 0 to infinity, of negative 1 to the k, 0 to the 2k plus 1, over k factorial, 2k plus 1. Now notice that in this term, every single term is multiplied by 0. Even when k is 0, we have 0 to the first power. So every single term in here is equal to 0. And the sum of 0, 0, 0, 0, 0, 0, 0 is going to be 0. So we're left with just figuring out what this sum is. Well, note that, no matter what power we raise 1 to, we get 1. This sum just becomes the sum k goes from 0 to infinity, negative 1 to the k over k factorial 2k plus 1. And we want to figure out, what that number is to within 10 to the negative sixth. Before we can even ask that question, we should ask, well, does this series, that's what we have now, right? Does this series actually converge at all? Well, we need to use one of our convergence tests to answer that question. Let's look at the alternating series test, because this is an alternating series. It has a negative 1 to the k on top. K factorial is always positive, so it's 2k plus 1. So that would give us an a sub k equaling 1 over k factorial, 2k plus 1. So what do we need for this? We need non-increasing and going to 0. So convince yourself that a sub k plus 1 is always going to be smaller than a sub k by looking at the terms. It would be 1 over k plus 1 factorial times 2k plus 1 plus 1. And we're comparing that to 1 over k factorial 2k plus 1. Well, k plus 1 factorial is bigger than k factorial, so that makes this smaller. And 2k plus 1 is bigger than 2k plus 1, so we also added a bigger thing to the bottom for that term, so that one also made the k plus 1 term smaller. So yeah, it is non-increasing, and if we look at the limit as k goes to infinity of the a sub k's, we can see the bottom goes to infinity, top is constant, so this is 0. So it converges by the alternating series test. And in fact, what's more than that, remember we have a remainder bound for the alternating series. Remember that we know then that the remainder, r sub n, is always less than or equal to a sub n plus 1, which is, in this case, we figured this out already, we called it k, but let's just call this one k2. So the remainder r sub k is less than or equal to a sub k plus 1, which is k plus 1. 1 over k plus 1 factorial times 2 times k plus 1 plus 1. So now, if we want an error of no greater than 10 to the negative 6th, we want to make this number less than 10 to the negative 6th. Since we know our error is less than that. Well, again, there's not a really great way to solve this, but just try to plug in a couple different numbers. And it happens to be if we plug in 8 for k, we would get 1 over 9 factorial times 19. And that's approximately 1.45 times 10 to the negative 7th. So that's less than 10 to the negative 6th. So we know if n is at least 8. But that's better than 10 to the negative 6th. We know if k is at least 8, then the error is less than 1.45 times 10 to the negative 7th, so it's less than 10 to the negative 6th. So we can say that the integral we were trying to estimate, and this is a definite integral, the answer should be a number, and it might be a number we actually needed to know for some reason, is approximately the first 8 terms here. So that would be 1 minus a third plus 1 over 5 times 2 factorial minus 1 over 7 times 3 factorial plus 1 over 9 times 4 factorial minus 1 over 11 times 5 factorial plus 1 over 13 times 6 factorial minus, let's see if we can squeeze this in here, 1 over 15 times 7 factorial plus 1 over 17 times 8 factorial. And that number ends up being approximately 0.7468242657. So we were able to find a numerical answer to this integral, even though we couldn't find an antiderivative except for as a power series. All right, now we want to find a series representation for pi using the fact that arctan of 1 is equal to pi over 4. And then we want to use this series to approximate pi to within 10 to the negative 2. So 3.14, right? That's what we're trying to get to. But let's see if that actually works. Well, how are we going to do this? If we know that arctan of 1 is equal to pi over 4, well, we want to find out about pi, right? So that would mean that pi is equal to 4 times arctan of 1. But we have a power series for arctan, right? So this would mean pi would be equal to 4 times the power series for arctan. Now remember what that is? That is negative 1 to the k over 2k plus 1 times x to the 2k plus 1. But in this case, we want to plug in 1 for x. And that's going to be nice enough to go away for us. So this would mean that pi is equal to 4 times the sum. Oh, we should put in the bounds here. So k goes from 0 to infinity. So then pi is equal to 4 times the sum k goes from 0 to infinity of negative 1 to the k over 2k plus 1. And we can bring the 4 inside. So we get a power series or to get a series, it's not a power series anymore, there's no x. To get a series representation for pi, we would get pi equals the sum, k goes from 0 to infinity, of 4 times negative 1 to the k over 2k plus 1. So that's great. And then we want to know, can we actually find a number from this? Obviously, the more terms we put in, the closer and closer we're going to get to pi. But what do we know about it? We do know that, notice that this is again an alternating series because it's negative 1 to the k. 4 is always positive. 2k plus 1 is always positive. If we can show that it's not increasing and going to 0, we have that theorem about the remainder again. So, non-increasing, so then we say that a sub k plus 1 is always less than or equal to a sub k. Well, we would have 4. Maybe we should write down what a sub k even is first. So a sub k is going to be 4 over 2k plus 1. So a sub k plus 1 is going to be 4 over 2 times k plus 1 plus 1 less than or equal to 4 over 2k plus 1. So notice putting the k plus 1 over here in the bottom made the whole bottom bigger, which made the thing smaller. So yes, we believe that. And if we take the limit as k goes to infinity of the a sub k's, we can see that that goes to 0. So we're allowed to use our information about our remainders for alternating series. So we know that the absolute value of the remainder for the kth term is less than or equal to the absolute value of a sub k plus 1, which was equal to 4 over 2k plus 1 plus 1. And now we want to figure out what that means for n. There's no weird factorials or anything here. All we want to do is make this number be less than 10 to the negative 2. So let's see what that means for k. So 2k plus 1 plus 1, that's going to be a positive number, right? So let's move it to the other side. 4 less than 10 to the negative 2 times 2k plus 2 plus 1. 10 to the negative 2, that's the same as dividing by 100, so moving it to the other side, that'd be 4 times 10 to the positive 2, or 100, being less than 2k plus 3. So 400 less than 2k plus 3, 397 less than 2k, or we need k to be bigger than 397 over 2, which, dividing that out, that is 198 and a half. So if k is 199, we'll make sure that our error is small enough. So we would have to add up the first, essentially 200 terms to get within 10 to the negative 2, to get 3.14. All right, now it's asking us to compute the sum of this series. We want to recognize this as some function with some value plugged in for x. Well, notice we have a 2 to the k minus 1, so maybe let's think that 2 is plugged in for x. So let's consider the series k goes from 1 to infinity, k over k plus 1 factorial, x to the k minus 1. And remember, that would mean we would care about that with x equals 2. Okay, so now we have a series, a power series, and if we can figure out what function it is, then we could plug 2 into that function and find the sum of the series that we want. So what do we know about this? Well, notice that it has the form something, in this case 1 over k plus 1 factorial, times k x to the k minus 1. This kx to the k minus 1 should look like something to you. It should look like the derivative of x to the k. So instead of looking for this series, let's look for the series k goes from 1 to infinity of 1 over k plus 1 factorial x to the k plus some other constant, because we don't know what the constant is. And that's what we get when we find the integral of the series we had before. Then notice that if we multiply that through by x, so x times the integral of, let's call the series we want to find f of x. x times the integral of f of x. So that's going to give us x times what we had before. The sum k goes from 1 to infinity. 1 over k plus 1 factorial, x to the k plus c. And why am I doing this multiplying by x? Because I want to make the power of x here k plus 1, so it matches the thing in the factorial. So this becomes the sum k goes from 1 to infinity of x to the k plus 1 over k plus 1 factorial plus c times x. With an index shift, we get the sum k goes from 2 to infinity of x to the k over k factorial plus cx. But now we recognize this. We know, off here to the side, we know e to the x is the sum k goes from 0 to infinity of x to the k over k factorial. So we can rewrite this as the sum k goes from 0 to infinity, x to the k over k factorial. What have we added in that we've added in the first two terms? So minus the first term there is 1, and minus the second term is x to the 1 over 1 factorial. So that'd be x plus dx. Now we can replace this series with e to the x. So this is e to the x minus 1 minus x plus cx. Remember that was equal to x times the integral of the function we're trying to find. So if we're trying to find f of x, let's divide both sides by x. So the integral of f of x is going to be e to the x minus 1 over x minus 1 plus c. And then taking the derivative of both sides, we're going to get that f of x was e to the x minus 1 over x's derivative. And then both 1 and c are constants, so they go away. And so what we get when we take the derivative is the derivative of the top, which is e to the x, times the bottom minus the top, times the derivative of the bottom, all over the bottom squared. So simplifying, we get x e to the x minus e to the x plus 1 over x squared. And note here that this obviously doesn't make any sense when x is 0. But what we really cared about, remember what we wanted in the first place was when x was 2. So f of 2 is 2e squared minus e squared plus 1 over 4. So whatever number that is, that's the number that we're looking for. All right, now we'd like to identify the function represented by the power series. And here the power series is the series from k goes from 0 to infinity of x plus 3 to the k over k factorial. Well, this looks like a series that we know. We know that e to the x is the sum k goes from 0 to infinity of x to the k over k factorial. So we'd like to just make a substitution, u equals x plus 3. And the question is, are we allowed to do that? Well, we can do that if x plus 3 is in the interval of convergence. But the interval of convergence here is negative infinity to infinity. So yeah, that'll work. So what does that mean? That means that if, we replace this with u, we would get e to the u, so we get e to the x plus 3. Let's do one more of these. Identify the function represented by the power series. Now we have 3k x to the 3k. And here we want to recognize that by having this k out front, it should make us think about derivatives. So what was the derivative of x to the 3k? That'd be 3k x to the 3k minus 1. Since k is a constant here. And that's kind of what we have. We have a 3k x to the 3k. So we have actually x times that, right? So we have x times the derivative of x to the 3k equals 3k x to the 3k. All right, good. So then what does that tell us? That tells us if we look first at the sum x to the 3k, k goes from 0 to infinity. We know what that is. That's a geometric series with x cubed being the r. This is 1 over 1 minus x cubed. Now, to get our series, we want to first differentiate this. So let's differentiate both sides. We would get the sum k goes from 0 to infinity of 3k x to the 3k minus 1. And that's going to equal 3x squared over 1 minus x cubed to the second power. And then we want to multiply both sides by x. So we get x on this side, gives us the series we're trying to find, 3kx to the 3k. And x on this side gives us 3x cubed over 1 minus x cubed squared. And that is the function that is represented by this power series. Now, of course, we have to worry about interval of convergence. So remember, this works if the thing we're substituting in is within the interval of convergence. So the interval of convergence for a geometric series, remember, is r less than or equal absolute value of r strictly less than 1. So we said this was a geometric series with r equaling x cubed. And so we have x cubed, absolute value less than 1, which means x is an absolute value less than 1.